Okay, now we're going to apply this theorem. We didn't apply it last time. We talked about what it means, make sure that's a 1. And then we want P and Q to be analytic, meaning continuous. And you try not to include the discontinuity in your solution, except now you're looking for a radius. It looks slightly different, so let me elaborate with the first example I have. The first one is really straightforward. I do notice that that is 1. And I notice P is 4 and Q is 6x. They're continuous everywhere. And they say, what if we start initially at 0? Well, since there's no continuity, I could have, and they call it rho for the radius, it could be infinite. And what if you started at 4? Well, that's not going to matter. It doesn't matter where you start. There is no restriction. That is infinity as well. Alright, so since it's continuous everywhere, kind of like when we did the interval, figure out where the interval for the solution exists. Here it exists everywhere, but now we're doing that in general case. How about this problem? I notice this is not a 1, so I need to divide by that. If I divide by that, y double prime plus 4x over 1 plus x cubed y prime plus 1 over 1 plus x cubed y equal to 0. So now we know this is analytic everywhere except for this equals 0. Where would x cubed plus 1 equal 0? That's when x plus 1 into x squared minus x plus 1 equal to 0. X equal negative 1, so x cannot be negative 1, and x squared minus x plus, I'm going to complete the square, minus 1. Take half of the middle number, which is 1/2, and square it. That makes this x minus 1/2 squared equaling negative 3/4. And that would mean that x equals 1/2 plus or minus radical 3 over 2i. So, negative 1 is not allowed. So the red is what I can't have. Let me center those. There we go. So we could count properly. So, negative 1 is not allowed. You can't include that. F is not analytic at that point. If I take this point, isn't that really 1/2 radical 3 over 2 and 1/2 negative radical 3 over 2 in the complex plane? This is the real, this is the complex. So if I go 1/2 to the right and radical 3 over 2, which is about 0.9, and 1/2 and minus 0.9. So those are the analytic points. If I choose my x to be 0, well, let's see how far I could go. I could move as far as those points. Actually, I could do a better job than that. There we go. I can't exceed those points. The farthest I could go is really that far. And if you look, this here is 1, this here is 1, and this here is 1. So rho equal 1 in this case. What if I chose the initial point to be at 2? So if I starting at 2, how far can I go? Well, let's see. I can't have a negative 1. I can't have 1/2 plus radical 3. I can't have 1/2 minus radical 3. If I started expanding a circle around this point, it seems I can go as far as those 2 points. I can't exceed those points. Well, that means I need to know what this distance is. This point is 2, 0. So if I figure out those are equidistant, if I figure out what this is, well, let's see. If I go on this triangle and figure out the hypotenuse, right, this is 2. So 2, 1/2 to 2, that makes this 3/2. And I know this height is radical 3 over 2, so I could say that r squared equals radical 3 over 2 squared plus 3/2 squared. R squared will equal 3/4 plus 9/4. That is 12/4, which is 3. And if I square root both sides, I'll get R to equal radical 3. So in this case, the farthest I could move away in all directions is radical 3. And as long as rho is radical 3, this function, this differential equations will be analytic, and my solution would make sense. I can't go beyond that. I can't include any of those points. Later on, we call them singularities, but who's counting? And here's another problem. Problem number 7. And here it says go back to section 5.2, go through 1 through 11. I picked number 6. So this number 6 is from section 5.2. This is extra practice. And determine the lower bound, the same deal. I noticed that this is not a 1. So what I'm going to do, I'm going to make it a 1. I'm going to divide both sides by 1 over 1 minus x. So I know that 1 minus x equals 0. So x cannot be 1. If I go to 1 and I mark 1 as a singularity, then I'm looking at the problem. They're saying, what if you started at 0? Well, if you start at 0, do you see that the farthest you could go from 0, you can't go beyond 1? So that means rho equal 1. Now, I'm going to match the answers for you in the back of the book. Give me a sec. And this is really how the answers are going to look. So for number 1 in the back of the book, they call 1A, 2B, 3C. We did number 6. If you look in the back of the book, the answer to that is look at part F and you'll figure that out. You'll know what that means once you look at it. Now we're going to look at first order equations. The series method discussed in this section are directly applicable to first order linear differential equations in this form. And of course, what we're going to do when we're going to start this, we're going to make sure that we're with P of x, Q of x, and at a given point, the function P equal Q over P. Well, if you just set that equal to 1, everything will match accordingly, just like we did. That's what they're doing here. So if you set that equal to 1, you really don't have to worry about all of this manipulation that they do. They say this has a Taylor expansion, meaning if I take y prime plus if I divide by p, wouldn't the equation look like that? Would that be in a 1? They're talking about this right here is actually this right here. So we know what that is already. So it says such a point is called an ordering point, and further, the radius of convergence for this series is at least as large as the radius of convergence, which is what we just found. No biggie. Now they say of this Q over P, meaning wherever P is not 0. In number 13 through 16, solve the given differential equation by series in power of x and verify that a sub 0 is arbitrary in each case. In problem 17 involves a non-homogeneous differential equation, and we're not going to go that far. I just want you to get a feel of what this is, and that's what we're going to start with on 5.2, 5.4, 5.5, and chapter 10. So here we know how to solve this. We're going to solve this 2 ways. They want us to show that. What we're going to do, we're going to let y equal the series n equals 0 to infinity of x to the n, 8 sub n x to the n. So this is going to be a bit lengthy, just bear with me. And from 5b, we know that y equal a sub 0 plus a sub 1 x1, a sub 2 x2, a sub 3 x3, and the list goes on. I need to know when I take a derivative, if I lose any terms, wouldn't that become 0 plus a1 plus 2a2 x2 plus 3a3 x3? So I noticed that I lost a term. When I take a derivative, I need to boost the index 1 up because I lost a term. And the derivative, as you did back in the days in 5b, and if not, here it is, you simply bring the power down, subtract 1 from the power. There it is. And now all what you're supposed to do is go in here and say, well, this is the series n equal 1 to infinity n a sub n x to the n minus 1 minus x times, and the series is right there. That is series n equals 0 to infinity a sub n x n, and that equal to 0. And in 5b, I keep on saying 5b, I don't know if your teacher did that. I do that for my students because of this class mainly. The goal right now is to figure out how to get it to equal 0, and do remember, as series equals 0, this series equals 0 if the coefficient equals 0. X equals 0 is meaningless. That's always a solution. If I put x equals 0 there, I'll always get a solution. So I need to figure out for what values of a sub n would this be 0. I need to combine those. So first off, I need those to match. I need this power and that power to match. So before I get excited and start manipulating things, let me write out the series as it is. When you distribute that n, that becomes the series n equals, that's a 0, right? Right there. 0 to infinity, a sub n x to the n plus 1, and I want that to equal 0. So now this is how I'm going to fix that. I am going to fix that by making this x to the n. So if that's x to the n, that's going to shift 1 down, a sub n minus 1. To compensate, this has to go up. And again, you could check that by throwing a 0 in there and a 1 in there and see that you get the same first term, a minus. And here, I'm going to boost this one up to make it x to the n. Of course, you could make this n minus 1 and save yourself some time, but for now, I'm going to take my time with this because this is an introduction. And to compensate for that, again, if this went up by 1, this needs to go down by 1, and there it is. So the first order of business, make sure those are the same so you could combine them. The next order of business is for me to figure out how am I going to do this. Well, those don't match, that's okay. Throw n equals 0, that will make this a 1, a sub 1, plus the series n equal, if I threw 0 n 1 to infinity, n plus 1, a sub n plus 1 x to the n, minus the series n equal 1 to infinity, a sub n minus 1 x to the n equals 0. Now I can combine those, a sub 1 plus both series match, n equal 1 to infinity, and I take x to the n out of those, kind of like factoring. What's left? N plus 1 a sub n plus 1 minus a sub n minus 1 equal to 0. Again, x equals 0 is meaningless. So the way this works, I need to get a 0, I need a few things to happen. One, I need a sub 1 to equal 0. That's how I can get it to be 0. And on top of that, I need n plus 1, a sub n plus 1 minus a sub n minus 1 to equal 0. And if I solve that for a sub n plus 1, I'll get a recursive formula stating that a sub n plus 1 equal, move that to the right, divided by n plus 1. So, if I look at how this works, and remember, I'm just going to remind you of this because you might not have seen it. If you haven't, here it is, something that's going to save you a lot of pain in the long run. Think of the domain of those is always integers. It can be a fraction. If I say this is n, the next integer is n plus 1, and the previous integer is n minus 1, make that a subscript. So anytime I'm talking about a term, this is the next term and this is the previous term. It's good to think of it in terms of that. And I already started with a sub n equal, a sub 1 equals 0. Well, let's see. If I go for a sub 2. A sub 2, that means you put a 1 right there, right? A sub 2. If you put a 1 right there, that's a sub 0 divided by 2. Well, got it. Very good. How about a sub 3? A sub 3 is if you put a 3 there, right? I'm sorry. A sub 3, that means you put a 2 there. Put a 2 there, that's a sub 1 divided by 3. But a sub 1 is 0. So that's 0 over 3. That's really 0. Very good. I'm going to go for a sub 4. A sub 4, I'm trying to figure out a pattern. A sub 4, if you put a 3 there, that becomes a 4. 3 in there, that's a sub 2 divided by 4. But a sub 2 is right there. That is 1 over 4 times a sub 0 over 2. That is a sub 0 over 4 times 2. And I'm going to do a few of those until I figure out a pattern. A sub 5, to get an a sub 5, I must put a 4 there. 4 plus 1 is 5. A 4 in there will make it a sub 3 divided by 5. But I know that a sub 3 is a 0. So that's going to be 0. So it seems all the odd terms are 0, which equal a sub 7, which equal a sub 9. No need to find those anymore. How about a sub 6? To get a sub 6, you must put a 5 right there. 5 plus 1 is 6. That's a sub 4 divided by 6. But a sub 4 is right there. That's 1 over 6 times a sub 0 over 4 times 2. That is a sub 0 over 6 times 4 times 2. Let's see if we got the pattern. Can you guess what a sub 8 is? Well, look at that. A sub 2 is a sub 0 over 2. A sub 4 is a sub 0 over 4 times 2. A sub 6 is a sub 0 over 6 times 4 times 2. A sub 8, I'm guessing it is a sub 0 over 8 times 6 times 4 times 2. If you don't see the pattern, you need to do a few more of those until you figure that out. And now if I go back to my original substitution, which is right, I cluttered all of these. Right there, I let y equal that. So if I write y as I did right there, because that's what this is, now I'll be looking at y equaling, and I'm going to list a few of those. A sub 0 x a sub 0 plus a sub 1 x to the 1 plus a sub 2 x to the 2 plus a sub 3 x to the third plus x to the 4, a sub 5 x to the 5. We went to 8. Let's go to 8. And of course, this is infinite. I already concluded that the odds seem to be all 0. If that coefficient is 0, all of these odds are 0. I'm really looking at a sub 0 plus a sub 2. What did I get a sub 2 to be? It's right there. That is a sub 0 over 2x squared plus I got a sub 4 to be a sub 0 over 4 times 2x to the 4th plus a sub 6, a sub 0 over 6 times 4 times 2 x to the 6th, and a sub 8 is a sub 0 over 8 times 6 times 4 times 2 x sub 8, and the list goes on. And if I factor an a sub 0 out, I notice there's a 1 plus x squared over 2 plus x to the 4 over, this is 2 squared, and this is really 2 factorial. Plus, if I take x to the 6 over, and let's see how this works. 6 times 4 times, well, 6 is really 3 factorial, and that is 2 times 2 times 2 is 2 cubed, plus x to the 8 over, and if I look at the combination, so 4 factorial is 12, that's those right here. That will give you 4 factorial. You're left with 2 to the third times 2 squared. That's 2 to the fifth. And this list goes on. So I would say y equal a sub 0 plus a sub 0 into 1 plus x squared over 2 to the 1 plus x squared over 2 squared over 2 factorial, simple algebra, plus x squared over 2 cubed over 3 factorial, plus x to the 4 over 2. Let me think about that one really quick. That didn't work. Why is that? Let me just check really quick. Oh, I see why that didn't work. Because 4 factorial is actually 4 times 3 times 2 times 1. That's 24, not 12. I made a mistake. So this right here, if I really want to get a 4 factorial out of that, I need a 24. That's the product of those. 2 to the third times 2 is 2 to the fourth. There you go. Very good. Over 4 factorial. And isn't that a sub 0 times the series n equals 0 to infinity of x squared over 2 to the n over n factorial? And don't we know what that is? Isn't that e to the x squared over 2? And how do you know that? Well, we did look at section 11.9, 11.10. There's a table associated with that. And now what? Now I want to show you that it's the same answer. We're doing a simple problem because calculus is not going to be able to solve what's to come. We need to solve things, equations in series. Suppose I have this equation right there, and I want to solve it. Well, can't you say dy dx is xy? Wouldn't that mean dy over y equal x dx? And you integrate. Doesn't that mean that natural log of absolute value of y equal x squared over 2 plus c? I don't like that too. And wouldn't you say y equal e to the x squared over 2 plus c? Wouldn't that mean y equal some c1 e to the x squared over 2? Of course, it's a lot easier to solve the problem this way. This is just an introduction. And you have one of those on the homework. So 5 and 7, you're going to figure out where is this analytic, like we did. And 13 is identical to this. Make sure you spend enough time on that and get that out of the way.